Hi students, welcome to Team Curiosity e-learning classes. In this video, we will derive the equation for the elevation in boiling point of a solution when a non-volatile solute is added to it. First of all, let us consider a graph of vapor pressure versus temperature for a pure solvent and for which we obtain a curve A. After adding two different amounts of non-volatile solutes to the solvent, we get two different curves named B and C. Now, if we consider the points T0, T1 and T2, we can see that these three curves nearly become straight lines, assuming the two solutions to be nearly dilute, where T0 is the boiling point of pure solvent, T1 is the boiling point of solution 1, and T2 is the boiling point of solution 2. Since triangle ACE and triangle ABD are similar, by the similarity theorem we can write AC by AB is equal to AE by AD. This implies that T2 minus T0 by T1 minus T0 is equal to P0 minus P2 by P0 minus P1. Here, we can denote the change in temperature and pressure as delta T and delta P respectively. So, this implies that delta T2 by delta T1 is equal to delta P2 by delta P1. Hence, we can say that delta T is directly proportional to delta P. That is, the variation in boiling point of the solution is directly proportional to the variation in vapor pressure. Take this as equation 1. Now, we had studied earlier from Raoult's law, P0 minus Ps by P0 is equal to Wb into Ma by Mb into Wa, where Ma is equal to molecular mass of the solvent, Mb is the molecular mass of the non-volatile solute, Wa is the weight of solvent present, Wb is the weight of non-volatile solute, P0 is the vapor pressure of the solution in pure state, and Ps is the vapor pressure of the solution when a non-volatile solute is added to it. Taking P0 to the right side, we get P0 minus Ps is equal to Wb into Ma by Mb into Wa whole into P0. It signifies that P0 minus Ps is proportional to Wb by Mb into Wa, taking P0 and Ma as constant terms. From equation 1, we got that delta P is directly proportional to delta T. So we can write delta P is directly proportional to delta T, which is again directly proportional to Wb by Mb into Wa. This implies that we can write delta T is equal to K whole into Wb by Mb into Wa. Take this as equation 2, where K is the elevation constant. Now let us consider three cases. Case 1. Let Wb by Mb is equal to 1 and Wa is equal to 1 gram. Then from equation 2 we can write delta T is equal to K. Now consider case 2. Let Wb by Mb is equal to 1 and Wa is equal to 100 gram. Then from equation 2 we can write delta T is equal to K by 100, which is again equal to K dash. This implies that K is equal to 100 K dash. Take this as equation 3, where K dash is the molecular elevation constant. Now, putting the value of K from equation 3 in the equation 2, we get delta T is equal to 100 K dash whole into Wb by Mb into Wa. Take this as equation 4. Again, let us consider case 3. Let Wb by Mb is equal to 1 and Wa is equal to 1000 gram. Then, from equation 2, we can write delta T is equal to K by 1000, which is equal to Kb. This implies that K is equal to 1000 Kb. Take this as equation 5, where Kb is the molar elevation constant, or we can say that Kb is the elevation in boiling point produced when 1 mole of solute is dissolved in 1000 gram of solvent. Now, putting the value of K from equation 5 in equation 2, we get delta T is equal to 1000 Kb into Wb by Mb into Wa. This implies that delta T is equal to molality into Kb, where 1000 into Wb upon Mb into Wa is the molality. Take this as equation 6. Therefore, we can conclude that the elevation in boiling point of a solution is directly proportional to its molality. And also, the equimolar solutions of all the substances in the same solvent will show equal elevation in boiling points. So, equation 6 is the equation for the elevation in boiling point of a solution caused by adding a non-volatile solute to it.